galaxy formation and evolution in the context, or what is the impact of dark matter in galaxy formation and evolution. And in the first talk, I will basically describe the main ingredients of what is known as the standard model of structure formation. In the second lecture, I will give some motivations as to why this standard model is limited and it needs to be extended, at least for the sake of being complete when it comes to the level of structure formation theory. And in the last discussion session, I will just give my perspectives on the future, where this field is going in the future. So, of course, as we heard, or as we know, most of the, well, all the evidence we have of dark matter is gravitational, and we already saw some of the evidences, so I will not stop too much into them. It's enough to say that we believe that through this evidence that we have built up at different scales and different times, we have come to believe that approximately 80% of the universe is dark, of the matter in the universe is dark. Now I will just stop in one. This, of course, this evidence comes from the CMB, for example, the properties, statistical properties of the CMB, or the properties of galaxies. So I will not give too much detail about that, but I always, since a year or so, I want to put this picture because I think it's very nice. And in a single picture, you see a nice effect of GR, which is lensing, and you also see evidence of dark matter. So this is a cluster of galaxies. Here, there is, of course, lensing the light that is coming from the background galaxies, and it's creating, for example, weak lensing here, distortions, it distorts the shapes of the galaxies, and it's also creating strong lensing. So that means that it's creating multiple images of the background galaxies. And one of them is here. You can see here is one galaxy, this is the same galaxy, and this is another one. So it's three images of the same galaxy. This is a very massive cluster. And what is nice about this one is that in one of them, in one of these galaxies is actually being lensed by an elliptical galaxy within the cluster. And that lens is creating here, in one of the spiral arms of this galaxy, spiral galaxy that is in the background, a supernovae went off. And the elliptical galaxy is creating an Einstein cross, or a lensing of that supernovae. So a multiple image of that supernovae that you can here see in the zoom. So that's 1, 2, 3, 4 images of the supernovae. So I mean, why this is nice? Well, of course, this is a very special configuration of lensing and a very well-known GR effect on top of created by the presence of dark matter. Of course, any type of model that tries to explain dark matter needs to also get to the level of explaining this kind of observations. And this in particular is nice because it has these multiple images. You can model the distribution of dark matter here and make a prediction that the supernova should be seen now here in between 2015 and 2020. That was predicted in 2014 that it would appear somewhere there because of this time delay, right? That is because the light passes different paths basically as it travels toward us. And last year in December, that was indeed what happened. So this supernova was predicted to appear here, and it predicted here. So just a nice illustration that I want to show, just the kind of level of exquisite data that we have that we need to explain with any given dark matter theory. Another important aspect of why dark matter is important, in particular for galaxy formation, which is the focus of my talk, is of course that is in many ways is seemingly what we need to explain how galaxies came to be. Particularly, we know that the CMB represents an image of the universe when it was very homogeneous, but that degree of anisotropies that we can see in the CMB, which was at the order of 10 to the minus 3 in matter, needs to grow somehow into the structures, the large-scale structure that we see today, that has density contrasts that are of the order of 1. And ultimately, of course, we need to explain how galaxies such as Andromeda, that have a very, very high density contrast, came to be from these initial conditions. So this is really the goal of what is known as structure formation theory. How do we come from here to here? And of course, for that, dark matter is very important. So in this first lecture, I will just give the main ingredients of this structure formation theory, because I think it's very important to have them, to give you a flavor of that. And I will try to emphasize what I believe are the key points that can give us a hint about the dark matter nature. So the elements are, just say very briefly, you have a background evolution, and that's essentially very well known and established. You start with basically just one principle, which is the cosmological principle, and then you assign a metric, the Friedman-Robertson-Walker metric, and then you arrive to the Friedman equations, and that essentially gives you the background evolution of your universe. And of course, the parameters in that evolution, the amount of dark matter, the amount of ordinary matter, radiation, etc., they are constrained by observations such as the CMB. And structure formation theory really begins by, as I was saying, the point where this background is perturbed by these small density fluctuations that are seated in the CMB. So you have density fluctuations. So I'm going to talk about this delta a lot. So this is just the difference between the actual density and the background density divided by the background density. So it starts, the structure formation theory starts at the point where this delta is much less than 1. This perturbation is very, very tiny. And the ingredients begin when trying to, you have your initial conditions that are again constrained by the CMB. You have that observable that tells you the statistical properties of the universe at the time of last scattering. And then you again assign a metric, in this case it's just a perturbed Friedman-Robertson-Walker metric, and then you make some assumptions, for example, that you have an ideal non-relativistic dark matter fluid. And this is the most important assumption that has become the standard model of structure formation, which is called the cold dark matter hypothesis. All of you have heard about this, but it essentially means that this dark matter fluid is, once you produce it in the early universe, it freezes out, and after that essentially behaves as a collisionless fluid that has this property, which I will explain in a second, free streaming length, which is much smaller than characteristic galactic scale. So this is my way of defining what this hypothesis means, the cold dark matter hypothesis. This free streaming length is just the length or the scale that that the dark matter can travel before becoming non-relativistic. So when it was moving very, very fast, even if there are these inhomogeneities at very small scales, if the dark matter is moving very fast, it's able to erase the perturbations just because by random motions, essentially, the dark matter that are in overdense regions, they move to underdense regions. So the point, or really the hypothesis of CDM is that dark matter is collisionless, so all that matters is really gravity, and that this scale is very, very small, irrelevant basically for galaxy formation. So once you have those two hypotheses, then you essentially start with what is known as linear perturbation theory. So again, this is when you have these density fluctuations very, very small, and then you can make a treatment that is essentially analytical. So you can solve the growth of perturbations as a function of time within these assumptions, and you actually have almost no free parameters. I will describe in a moment what I mean by that. So what you typically do is, because you are in this linear regime, so the equations look linear, the equations that you have to solve, you can treat them independently. You can make a decomposition of the density fluctuations in plane waves. So in K mode, so this is essentially as treating perturbations of a given scale independently. And you can do that because you are in this linear regime. So at the end, really, you are dealing with equations. You can do, of course, this with the full general relativity prescription, but you can also do it in Newtonian gravity. That's okay. And essentially, you end up with these three equations: the continuity equation, the Euler equation, the Poisson equation, which we are all familiar with when it comes to fluids. And these equations really govern the evolution of the density perturbations, and what happens under the conditions that you have is something like this. This is the evolution you will have. The density perturbation starts growing, and as soon, there's a distinction there that maybe I should make, before the perturbations are causally connected. So this is what is known as the horizon, right? Before that, there's really, the scale of the perturbation is actually longer than the horizon in the universe. Then the treatment, I mean, you actually have to do this relativistically. But essentially, the perturbation grows, and once it enters the horizon, then there is a period where the perturbation grows in a way that is governed by a time where the universe, when radiation dominated the density of the universe. So there is a small, there is a period where the growth stagnates because of this dominion of radiation. And then afterwards, dark matter can grow once the universe becomes matter dominated. This is going to be more important in a second. But the important distinction here with ordinary matter is, of course, because it doesn't have any coupling with the standard model particles, and in particular with photons, it doesn't feel the pressure that the photons exert, for example, in ordinary baryons. And because of that, it can essentially grow freely just because of gravity. But of course, ordinary matter doesn't do that. And the protons, the electrons, everything is coupled together to the photons, and it's essentially pressure that prevents the perturbation from growing. That's why in the case of ordinary matter, you see these oscillations. So you have a period where the perturbation tries to grow because of gravity, but then the pressure opposes gravity and then expands, and then it collapses, and it creates these oscillations that are very important and actually have been seen. And these are known as baryon acoustic oscillations. They are seen both in the CMB, and they are seen in the distribution of galaxies because they are imprinted in the initial conditions, basically, of that distribution of galaxies. Afterwards, once the photons decouple from the baryons, then the gas or the baryons basically follow the dark matter, and then the process of galaxy formation can start. Now I stop in this quite a bit because I want to arrive to make this distinction, because this plot is going to become important in my second lecture, when I would argue that something similar to this can happen also to dark matter. At least it's allowed to happen. So this is why I stop here a little bit. Yes?
What is phi?
Yes, this is the gravitational potential. Yeah. Sorry, this is the Hubble parameter. Here you essentially, basically this is just conservation of mass, the Euler equation, and the Poisson equation. Yeah. And so I just talk about this evolution of a single perturbation. So you can think of this as a single, you have a region in the universe, and there is a region, say, of a given scale that is slightly more dense than the background. And that's the growth that I describe. And if you have another one slightly bigger, it's going to have a similar kind of growth, and one smaller is going to have a similar kind of growth. But of course, you need, if you want to study all of them at the same time, you need a statistical description. Of course, the CMB doesn't tell us the initial condition of our actual local universe. It just gives us a statistical description of what the conditions of the universe were at that time. And for that, so then we have to do a statistical treatment of this. And a way to do this is the way this is done is just to understand the clustering properties of dark matter by talking about certain characteristics of this of the density field. And one of them is, for example, with what is known as a two-point correlation function. So just to briefly give you a flavor of what this is, I mean, this is formally an average over this delta, which is the density perturbation, a two-point average. So you take, it's easier if I explain it here in the picture with an example. You can see very well, but this is essentially the actual distribution of galaxies in our universe. This is a recent 3D reconstruction from the SDSS survey. So these are actual galaxies. So you can think about these galaxies and say, well, they are distributed. Of course, you see just a projection here in the sky, but you also have redshift information so you can make a three-dimensional map of the actual distribution. And if you ask yourself, okay, how can I characterize the clustering of those galaxies? Well, you can take one galaxy and essentially compute what is the likelihood that I have other galaxies around compared to a random distribution. And that's really the two-point correlation function. It gives you a degree of how clustered your points, in this case galaxies or dark matter, whatever it is, quantity you are interested in, is how clustered they are relative to random. So now I mentioned this has been done for galaxies, and when you actually make the exercise and compute this two-point correlation function, you can measure it, and this is what you see. So of course, very close, the galaxies are very clustered, clumped together, so that's why the amplitude grows as you go to distances that are shorter relative. So this always, you are always comparing the distances between pairs of galaxies. And as you separate, of course, your clustering diminishes, and these are these baryonic acoustic oscillations that I was telling you about. So this scale comes exactly from the scale from the CMB, and from this balance between pressure and gravity that has actually been seen in the distribution of galaxies. So now, I gave this introduction to the two-point correlation function because it's common to measure the clustering of dark matter with something what is called the power spectrum. This is analogous to the power spectrum measurement that you see in the CMB, but this is for matter. And the power spectrum is nothing else than the Fourier transform of this two-point correlation function. So what I'm showing here is this power spectrum, which you can just think about the amplitude of your perturbations as a function of scale. Here, of course, is K. So these large scales mean small scales, and this is large scales. The initial conditions here are given by inflation that predicts basically a scale invariant power spectrum that would go like this. And as these perturbations enter the horizon and they become affected by this period of radiation domination that I was mentioning before, you have a deviation from the inflation prediction. You have this stagnation caused by this period of radiation dominated. And this is what is called the Mészáros effect. Here actually are these baryonic acoustic oscillations that I was mentioning before. And then as you go to smaller and smaller scales, you have this free streaming that I was mentioning. And this free streaming is going to depend on your nature, your dark matter particle nature, in particular, your mass. So if you're talking about a WIMP, a standard thermal WIMP of 100 gigaelectron volts, this free streaming length is roughly 1 parsec. So I wanted to arrive to this plot because this is basically the initial conditions for your structure formation theory. So this is the prediction for the linear regime of your structure formation theory. And this is what serves as an input for M-body simulations that follow the growth forward in time. And of course, I will talk a little bit more about this tomorrow, but there are constraints at large scales of how this clustering is, but all of this is free, so we don't really know how dark matter is clustered there. How do you proceed after that? As I said, you do it with M-body simulations. So just to remind you, you are always within this hypothesis that dark matter is cold and collisionless. And this, another way to think about it is basically saying, okay, I don't care what the dark matter particle is. All I care about is its gravity. And that's it. And that really has been the cornerstone, for the development of a structure formation theory in the last 20, 30 years. So how do you proceed from that? Well, in principle, you would need to solve the collisionless Boltzmann equation coupled with the Poisson equation. So this is also known as the Blasov-Poisson equation. So this is just telling you that because the dark matter is collisionless, the phase-space distribution is conserved. So gravity is just gonna stretch in time your phase space, wherever you have your initial distribution of dark matter in phase space, and that phase space can only be stretched, where it cannot be broken. That's essentially what it's telling you. Of course, if you know the phase space distribution, you automatically know the density field, and then you basically solve the whole problem, but you cannot really solve this equation fully. It's very hard. And of course, in practice, you can only really measure, you cannot measure this microscopically. You only measure it at a certain scale. So what an embodied simulation does is to discretize that phase space distribution with a set of particles that basically take mass. Each particle has a mass that is many orders of magnitude more massive than the actual dark matter particle. So this is one thing. The second thing is, of course, you put your density field, and then you essentially say that in a given point in space, the density field is represented there by a particle that has a given velocity. So you take your initial conditions that I was mentioning here before, this is the plot that I mentioned earlier, and then you try to create a realization of those initial conditions. And that's what you do with an n-body simulation. So this is basically this particle realization. Excuse me. Just turn this off here. So it doesn't look like that, but these particles here that appears like a scatter plot have essentially these initial conditions embedded there. And of course, in a simulation, you are going to have some restrictions. You are going to be restricted by the size of your your size of your simulation box, and by resolution. So the size of the box is going to limit how big the scales you can put into the computer, and the resolution is going to limit how small can you go into your density field or your phase space distribution. Let me skip this because this is probably too technical. And of course, you arrive to a simulation like this. Well, you have seen it before in the talk by Alejandro, but let me just, because I need some things to explain about this. Where is this? Then you start with something like this at redshift 50, and this is a representation. So each of the particles that are in the simulations have a color code that is connected to the local density around each of these particles. And as time goes by, gravity starts making things cluster together. And what is apparent is, of course, the formation of this large-scale structure that we have all seen before. And then, of course, gravity will act because you have it's not perfectly symmetric. It's going to tend to collapse first a dimension, so it's going to form like a pancake, and then another dimension, so it forms these filaments, and then finally the other dimension to form these nodes in the filaments, which are called dark matter halos. And a dark matter halo is just a self-gravitating structure of dark matter. And you see there is a lot of things going on, but there is nothing more here than gravity. So really the physics that is in here is very, very simple. What is complicated is just the number of particles that you need in order to be able to resolve the scales that you are interested in. In this particular simulation, they are actually simulating a structure that is supposed to be similar to our own Milky Way halo. So if this theory is correct, our Milky Way galaxy will be formed here in the center of this structure, surrounded by a huge dark matter halo, and embedded within that halo many subclumps. And that's actually the prediction of these models. And I will...
Sorry, so you are basically forming a grid, and each grid puts one particle that is integrating everything inside?
Yes, that's essentially...
So it's more general than taking mass of 100 GeVs, right?
Yes. Yeah, exactly. Yeah, so let me be more clear about that point. So once you are in the regime of simulations, this is what I meant, the cold dark matter has model of structure formation has no free parameters. So whether you have a particle that is 100 gigaelectron volts or more light, it doesn't matter for cold dark matter, right? As soon as you are within the scales of interest for structure formation, it doesn't matter. So just to summarize, you start with the initial conditions, you make an n-body simulation, you get nice pictures like this, which are essentially giving you the exact prediction of what the dark matter distribution should be within this theory as a function of time and as a function of scale. So you basically have solved the whole problem, and then you can, for example, compute this same quantity, the amplitude of clustering, as a function of a scale. This is the answer that the simulation gives you. And what you see here, these different lines, are basically that clustering compared to the prediction of the linear regime, which is these thin lines here, and as a function of redshift here. And what you see is, of course, that the nonlinear evolution, what it does is really enhance by many orders of magnitude the growth of structure, and this is just gravity acting, basically mixing the different scales to give that answer. So this is just a slide that I put with the state of the art. Well, this is really 2012, but just to give you a flavor of the kind of simulations we can do these days. These simulations go from galactic scales of the Milky Way, or let's say even smaller galaxies, to cluster scales, and of course cosmic scales of the order of 3 or 4 gigaparsecs. And the simulations have, now it's easy or relatively inexpensive to do simulations that have 1 billion particles, 10 billion particles. And the most recent simulations that actually was done recently has reached this trillion particle in a box. I think it has, it's 2 or 3 gigaparsecs, so this is just a representation. You see, this is a huge volume, and if you make a zoom, you can actually go and resolve clusters there. So it's really impressive, but this is more technological, or you want an improvement on the algorithms to solve the problem, but as I said, the physics is quite simple. Now let me just give some key properties of what is the finding of these simulations when it comes to the distribution of dark matter. So at the large scales, what we find, or what n-body simulations find, is actually an excellent agreement with the large scale structure of the universe that is observed. So if I hadn't put here the names, you wouldn't be able basically to distinguish this distribution by eye and these distributions here. But these ones are actually from the simulation, and these are real distribution of galaxies in the universe. So of course you can do this, you can quantify this and make, for example, with the 2-point correlation function, the actual clustering, right, to quantify it, and they agree pretty well. So it's very successful in that sense. Now, when you go to smaller scales, you really want to talk about what is the formation of these objects that I was referring to, these dark matter halos. Because you have this shape of your initial conditions, or if you want, the clustering of dark matter that is implied by the CMB, is basically telling you that because the scales that are smaller have a larger amplitude of clustering, they are going to collapse first, they are going to form or cluster together first, and you have this hierarchical growth of structures. So around redshift 30, 40 or so, you are going to have the formation of the first structures. So this is one of them, which are going to be the seeds of your larger halos that form by the accretion of these smaller ones. So this is just a cartoon of that. You form the smaller ones, and then they merge together into larger ones, larger ones, larger ones, until you form the massive, massive clusters. And this is actually essentially what you see in the simulations. Now, what you do with that information? Well, you want to get closer and closer to what you actually observe. And one simple observable would be just, okay, can you actually count how many of those objects you have? Just a counting thing. And of course, from the simulation, you will have a prediction what that abundance of halos as a function of scale should be. And this is a way to plot this. This is the abundance of halos as a function of their mass. And the prediction of the simulation, essentially forgetting about what happens here at the large masses, is that you have, here you see I'm plotting here m dn d log n m, so it's a bit complicated, but essentially it's telling you, it's giving you this prediction that the abundance as a function of mass is roughly a power law that is very close to -2 here. That's just the prediction of the model. And this is again when you have this in the standard scenario. Now I just want to mention this because not many people that work on the field are aware of this. The fact that we have these dark matter halos doesn't mean that all dark matter is inside the halos. There is dark matter, of course, that is outside. Even if you would be able to resolve the whole hierarchy and all the way to your the mass of your WIMP, you would still have dark matter that hasn't become part of one of these halos ever. And this is, for example, a prediction that was done, you could say, semi-analytically. So they essentially predict that this is, I think, a 100 giga-electron volt WIMP. So today, 80%, between 80% and 90% would be inside halos, but you have this extra. This is just a curiosity, but I think it's something that not many people are aware of. Of course, in the simulation, what you actually see is that only like 50% are inside halos and 50% are outside, but that's just a resolution effect. Anyway, so that's just a point. And this is a snapshot of the movie that I mentioned before. This is the kind of system, the kind of halo that you form. And you maybe are very familiar with this profile that is called the Navarro frame white profile. And this is just one part of the universality that you see in these structures. And this is just a point that I wanted to emphasize. So because you have only gravity acting there, the properties of these systems, these halos, are quite universal. And one of them is you can just simply see, okay, I take a system like this, I start in the center, and how is the density falling down as I go further and further away from the center. And this is what this plot is showing. It's a function of radius. And this shape is very universal. And it's essentially increasing. So as you go closer and closer to the center, the density grows and grows and grows. This is again a prediction of the model. Within this structure, another prediction, as I mentioned during the movie, is that you have all these clumps of dark matter that will be part of this larger structure. And these clumps in itself are basically like a copy of the bigger one. And of course you have this hierarchy of substructures and sub-halos and sub and so on that are essentially a copy and share the properties of the big ones with some important differences that I will just describe briefly here. This is just, I'm going to skip this. This is just a different way of looking at this in phase space. If you are curious, I can tell you about this later. I just want to mention two physical mechanisms that are important for subhalos. One of them is called dynamical friction, which you might be familiar with. I mean, this comes from Chandrasekhar. And in this case, you can imagine that when you have a mass and an object moving basically in a sea, say, of other objects that are smaller in mass, then it would tend to attract those objects, and this attraction will basically create this a way to intuitively understand what is happening. So it's moving like this. It attracts gravitationally the bodies, the particles, say, that are nearby, and they kind of create a wake here behind that exerts a drag into the moving object. And this is called dynamical friction. And why do I mention it? Because dynamical friction is a key thing when it comes to the formation of galaxies. So it's responsible in each of these clumps, in principle, a galaxy should be there. And once these clumps start orbiting inside the host, they suffer from this effect, and they will go and merge into the center. How much am in time? 20 minutes, okay. I'll try to be even faster than that, yeah. So the other one that I want to mention is tidal stripping. In this case, tidal forces can actually strip dark matter from from this substructure here and reduce its mass, and this is what is shown here. This is normalized, this is the mass, the fraction of mass normalized to the mass at infall, so when the substructure got inside the halo as a function of time, and as you can see, it quickly gets stripped away from its mass because of these tidal effects. And again, this is important also for galaxy formation, that's why I mentioned. So those two mechanisms are really what differentiates a substructure from a halo. I should probably, no, it's fine. One thing that I want to mention since we are talking about detection of dark matter is the local distribution of dark matter around the solar circle. This is particularly relevant for direct detection experiments. So you can also obtain the prediction in principle from the simulations, and what you need, of course, for direct detection experiments, you need to get a handle on the density around the solar system, the density of dark matter, and the velocity distribution. So from the simulation, you can extract that. Of course, it's always going to be resolution limited. And what I'm plotting here is, this is basically the probability distribution function of density as a function of, well, this is just the PDF of the density, basically. And what has been done here is you take one of these simulations and you put here a shell around the solar circle, and then you basically make many realizations around that shell. So this is like mimicking the position of the sun that is around 8 kiloparsecs from the center, and then you take the probability distribution function, and here is basically the density of the smooth component, and it has a tail that is connecting to substructure. So substructures are much denser because otherwise they wouldn't survive, but the likelihood of being in a substructure is small. So that means that taking that the halo is smooth for direct detection experiments is in principle okay, and this is the reason why, because the probability is very low. Of course, if you would happen to be, if we happen to live within one of these subhalos, then that would be obviously important for these detection efforts. It's just that the probability is low. Another thing that you need to care about is the velocity distribution. So how fast, what is the velocity distribution of dark matter particles? And the standard assumption there is, as we heard in the morning, is this Maxwellian distribution. Now how good as an assumption is, well, this is the actual distribution of dark matter particles here, and this is a Maxwellian. And these, you see, there are some strong deviations, but they are typically for direct detection experiments. Of course, it really exactly depends on the kind of target you are looking for, because if you are going to be sensitive to very high energies, then this might be more relevant, because the integral then becomes more sensitive to the details of your, how far you are from the Maxwellian. But if not, then the deviations are, I think, of the order of tens of percent or even less. But one nice thing about this, I want to stop here a minute, is that these bumps that you see here, that are deviations from the Maxwellian, are actually connected to the assembly history of your halo. So this means that in principle, if we were to detect, let's say, a WIMP, and then they become routine, right? So you could actually make a dark matter astronomy in that sense, that you could reconstruct from the experiment this shape, and then these bumps would tell you something about how our galaxy was formed, because this, as I said, these bumps are connected to how the halo was assembled. So I think that's quite nice. So finally, to close this first lecture, I want to talk about the huge elephant in the room, which is that we, of course, is not just dark matter, right? We observe the galaxies, and really the structure formation theory, although many people kind of end at this stage of saying structure formation theory just deals with dark matter. In reality, of course, you have to model galaxies. And this is important not only if you care about galaxy formation, then obviously it's important, but also if you care about the dark matter nature, because these processes affect how dark matter is distributed. And unfortunately, these processes are very complex. So this is just a schematic of all this. So I basically touch upon these ones. You have your cosmology, your gravitational instabilities, and the formation of dark halo, of halos. But then, of course, you have gas hydrodynamics, you have radiative cooling, you have star formation evolution, you have supernova feedback, you have black hole formation that also impacts, etc., etc. Then you have two halos come together, you form another galaxy, etc., etc. So all of that has an impact. So I will just mention a few of them that will be important in my lecture tomorrow. And with that, I will end this part of my lecture. So one of them, which is, well, I mentioned gas hydrodynamics, which I think this can essentially be crossed in the sense that I think we understand it well enough and it can be modeled good enough that it's fine, we have it under control. Now, radiative cooling essentially just means, it's just a cartoon of how a galaxy would form. As we understand the classical picture of galaxy formation, so you have your dark matter halo, then gas starts falling into this potential well, it heats up because of, this is basically collisional shocks, shock the temperature of the halo to the virial temperature associated with this dark matter halo, and then you have different processes, basically collisions between the ionized gas that is there that make the gas lose energy. And because it loses energy, it's going to collapse into the center, but it's going to do it conserving angular momentum. And that basically means it forms a disk. So this is just in less than a minute how these galaxies form. Why is this important? Because once the galaxy forms, of course, the dark matter is going to feel the gravity of that collapse of the disk. And if you have a distribution of dark matter as in this dashed line, so this is again the density of your dark matter halo as a function of radius, and just forget the many lines, but this is essentially this distribution of dark matter, and then you put a disk, which is this dash blue line, and then what happens is that dark matter responds to that disk that is forming in the center, and in the center actually the gravity that dominates is the gravity of the ordinary matter, and it pulls the dark matter density upwards. Now, this is something that I miss here, another plot, but I'm going to describe this other effect tomorrow, so yeah, sorry about this one. When you have supernovae, on the other hand, supernova is, well, this is the last stage of massive star evolution, and as they blow up, they release a huge amount of energy. And if the energy is released quick enough, they can actually affect, of course, they affect the gravitational potential in the center in such a way that can actually expand the dark matter. So I will describe this more in detail tomorrow. But this has the opposite effect. So instead of having, you start with something very dense here, which is the dash line, and once you include supernova, it actually goes down. So it's just to tell you that you have these competing effects that are mixing and complicating the picture of your nice M-body simulations that you had before. So what is the status of the structure formation theory right now? Well, we have a model that essentially is built upon this assumption. You can start from the initial conditions of the CMB and put essentially all these ingredients into a supercomputer under this assumption, and then you add all this physics that is known as baryonic physics in the community of galaxy formation, and then you end up just with something like this, and I will close my presentation with this movie, which is one of the state-of-the-art simulations of galaxy formation. So this is very similar to the one I mentioned before. Again, these are particles in a computer. This is roughly 100 megaparsecs. Time is going by. As I say here, this is part of this Illustris project. And what you will see is that right now you see, again, the dark matter is collapsing into these filaments and is forming these dark matter halos here. But soon you will start to see now the gas density. And star formation starts happening, and then all kinds of interesting things begin to happen. It should start very soon now. You can see there now, there are explosions there. So those are basically the supernovae exploding and removing the gas from the center and taking it and enriching the material around it, and also creating all kinds of course, mess here that affect the distribution of dark matter. And of course, this is very, very relevant for galaxy formation, but as I say, also for how dark matter is distributing in the universe. So this is the kind of things that we are able to do right now. This is a simulation that took 20 million CPU hours, so it's very, very expensive, but it's something that can be done, and I think it describes the state of the art. So we have a way to create a simulated universe in a computer based on this structure formation theory, and I think I will end here, and tomorrow I'm basically going to challenge the assumption that is behind these simulations. Thank you. Now that I changed to purple, this is actually metallicity. So this is the amount of metals. So metals in astronomy is just more than hydrogen. So for example, when it's very, very purple, it's very metal enriched. So it has a lot of metals inside. At the beginning, it was just the density of dark matter. Then when you saw the green, that's the gas density. Yes, and then when you saw the red, that's the temperature. It looked hot because it was basically the material heating up and going up. Yeah.
And then when did the metallicity must have been the second generation?
Yes, exactly. That's kind of the the second generation of stars. Yeah.
We have time for questions.
So what happens with this non-halo dark matter? Is it in the intergalactic space, or
Yes.
just like that? Do you have an idea of the density, or?
Yeah, it essentially has the background density.
Okay.
So this is the background material. I think what is surprising, or at least what surprised me, is that this prediction is really telling you that this dark matter basically never clustered. Mm-hmm. So you could understand that it's maybe not part of a dark matter halo. It can be a little bit away or expelled, but the prediction is really that it has never clustered. So it really is unclustered dark matter.
And another question: if you have more than one component for dark matter, you just average that to one mass or something?
Yes. So for the simulation, it doesn't really matter. Mm-hmm. So I will describe the two things that could matter in an n-body simulation. So when I say it doesn't matter, because structure formation really deals with the scales above, say, 10 to the 8 solar masses. So anything that happens below those scales is irrelevant, because it's not going to change this at all. So if you have any particle model that gives a prediction for the initial condition, this power spectrum that I described, that doesn't change it above 10 to the 8th, then you don't have to do anything. The problem is solved in a way.
And the interaction with an ordinary matter, if you have a WIMP, for instance, even if it's a small interaction, it doesn't affect this?
No, because the cross-section is weak scale. Basically, the mean free path is larger than the size of the visible universe, so it doesn't make any difference.
Just to know, which is the spatial resolution here?
I believe is, well, the actual interparticle separation, this is actually not particles. It looks like particles, but it's something that is called a moving mesh. So it's a grid, basically. So instead of dealing with particles, you put things in cells, in grids, and then you can apply similar techniques. But anyway, then the scale of resolution that you are thinking about is the size of your cell, and that's around 100 or 200 parsecs. But your true resolution is where you can trust the simulations. To which scale can you trust the simulations? And that's a more complicated question, because if you ask me just about the dark matter, the scale you can trust the simulations is around 500 parsecs. But once you introduce all this physics, then when you talk about resolution, you have to be very careful, because you move the resolution and usually you don't get the same answer. So the convergence is it's a hard thing to talk about in these simulations. So, just to answer briefly your question, it's around 500 parsecs, but that doesn't mean that these simulations give you the answer full bulletproof at 500 parsecs. Only for dark matter, for the gas and the rest, no.
I want just know about these. These are supernova events, no? What are you simulating?
Yes?
So I will know about this case in particular.
Yes, so,
Let's see. Okay.
yes. So actually you know that, of course, the supernovae operates at scales that are below that resolution. So this is called, what is called in the field, subgrid physics, they call it. So the way you simulate this is your cell, which is, say, 100 parsec, you put ingredients on that cell that are averaged at 100 parsecs in a way that you believe it represents the physics that occurs below that scale. So for example, supernova feedback would be simulated by, in those 100 parsecs, dumping the energy of the supernova you think exploded in the time resolution of your simulation at that scale. So that's one of the things that is very questionable about the simulations that I will also mention tomorrow.
Thank you.
More questions? So these supernova in the galaxy, so they can happen everywhere. So that the distribution then ends up, it's not symmetric, right? So that actually can be reproduced in the simulation. That asymmetry or...
In a way it is, but it's artificial because the way supernovae are produced here, of course, they are produced in the places where stars are formed. And stars are formed in the places where the gas density is higher. And these simulations use an empirical law to say where the stars will be formed. So in a way, they are already, they are already built to succeed in giving that answer.
Yeah.
Could you clarify that? You're saying that it's actually where you put the supernova is decoupled from the density?
No, it's quite coupled.
You put them right there where
Yes.
they are. You don't just put some average number approximately where they are.
Yes, yes. And of course, as I said, the supernova physics is not handled from first principles. It's handled in a way. Well, let me just take a minute to say this. Why this is an important problem to solve, and I think why this field is going to move in that direction, or is actually already moving. When you put the physics of stars and supernovae, you do it in a way that you have free parameters, because that's physics that is relatively uncertain, and you tune those parameters to match the properties at the scale of galaxies. So to, for example, you would say that such and such supernova had to be explode here to match the stellar mass or to match the metallicity of the galaxy, etc., etc. But those are much larger scales. Instead of actually saying, for example, am I solving the physics of the supernovae correctly? Yeah. So I think that's the big problem with this.
Okay, if that's it, then let's thank our speaker. I think that's it for today. Miriam, would you like to add something? We are only 45 minutes late over the